What a f-
911, what is your emergency?
The dawn of intelligent assistants. The journey of artificial intelligence has been one of relentless evolution, particularly evident in the transformation of AI agents. Many recall early interactions with chatbots, often characterized by frustratingly circular conversations and inability to grasp nuances, a common refrain being, "I'm sorry, I don't understand that." Fast forward to today, and the landscape is dramatically different. We are now witnessing the emergence of AI agents capable of not just conversing, but of managing complex business processes, learning from their environment, and proactively pursuing goals. This research delves into AI remarkable evolution, tracing the path from rudimentary scripted programs to sophisticated enterprise solutions, and explores the future trajectory of these intelligent systems. At its core, artificial intelligence is the broad scientific and engineering discipline focused on creating machines and software that can perform tasks typically requiring human intelligence. Within this expansive field, an AI agent holds a specific and crucial role. According to Stuart and Peter Norvig, an AI agent is an entity that can operate autonomously, perceive their environment, persist over a prolonged time period, adapt to changes, and create and pursue goals. This definition of the ambition inherent in AI agent development to create systems that are not merely reactive but proactive, adaptive, and goal-driven. I release videos sometime a while, but they all contain very important and in-depth insights about modern technological trends and how they transform our society, so you can apply this knowledge for your career or your business and get ahead of the crowd. Let's get started. Acting rationally. While early AI, particularly in the realm of chatbots, often focused on acting humanly, attempting to mimic human conversation to pass the so-called Turing test, the trajectory of modern enterprise AI agents align more closely with acting rationally. This means designing agents that act to achieve the best outcome, or in situations of uncertainty, the best expected outcome. The shift from mere mimicry to a focus on tangible, optimal results has been pivotal in the practical adoption and value generation of AI agents in the business world. The very components identified by Russell and Norvig, definitions such as autonomy, perception, persistence, adaptation, and goal pursuit, were not each element necessitated distinct technological breakthroughs. For instance, perception in textual context significantly improved with advances in natural language processing. Adaptation became a reality through machine learning, and true autonomy is being realized through sophisticated AI planning and reasoning capability. This implies that the evolution of AI agents has not been linear progression, but rather a convergence of multiple concurrently advancing technological streams. Understanding this evolutionary journey is paramount for businesses seeking to harness the full potential of AI today. The chatbot revolution. The lineage of today's sophisticated AI agents can be traced back to early experiments in human-computer interaction, most notably through the development of chatbots. These initial systems, while rudimentary by modern standards, laid crucial groundwork and sparked the imagination of what might be possible today. Rule-based chatbots. The story often begins with ELIZA, a program created by Joseph Weizenbaum at MIT in 1966. ELIZA simulated a psychiatrist by recognizing keywords in user input and reflecting statements back as questions using predefined scripts. Though its understanding was superficial, ELIZA's ability to engage in seemingly coherent dialogue was a landmark achievement, demonstrating the potential for computers in human-like interactions and initial interest in natural language processing. Following ELIZA, Perry, developed by psychiatrist Kenneth Colby in 1972, represented a step forward. Perry simulated a person with paranoid schizophrenia and was more advanced in maintaining a consistent persona and interacting with users based on more complex, although still rule-based internal model. Other notable early systems included Jabberwocky in 1988 and Alice, artificial linguistic internet computer entity, designed in 1995, which utilized IAML, artificial intelligence markup language, for more varied interactions. Their operational logic was based on identifying specific keywords or patterns and triggering scripted responses. Consequently, they were severely limited in their ability to understand nuance, handle ambiguity, or adapt to conversational flows that deviated from their programmed paths, often leading to rigid or nonsensical interactions. The inherent inflexibility and lack of scalability of these rule-based systems became a significant bottleneck, directly fueling the research and adoption of more dynamic and intelligent approaches to language understanding. The game changer: natural language processing. NLP is the branch of AI that empowers computers to process, interpret, understand, and generate human language, both written and spoken. Several historical milestones in text analysis and early NLP were pivotal. In 1950, Alan Turing's paper, Computing Machinery and Intelligence, introduced the Turing test, proposing a criterion for machine intelligence based on its ability to exhibit conversational behavior indistinguishable from that of a human. This laid the conceptual foundation for decades of research into AI and NLP. A significant early demonstration was the Georgetown IBM experiment held in 1954. This project successfully translated over 60 Russian sentences into English using a limited vocabulary of 250 words and just 6 grammatical rules. Despite its modest scale and simplicity of its rule-based algorithms, the experiment was a landmark event. Conducted at the height of the Cold War, its success in automated translation captured public attention and crucially attracted government and military interest in funding. It served as a vital proof of concept, demonstrating that computers could tackle complex linguistic tasks, not just numerical calculations. This early investment, driven by geopolitical imperatives, provided essential momentum for the nascent field of computational linguistics, the benefits of which would ripple out to chatbot development and broader NLP application years later. The limitations of purely rule-based systems led to a shift towards statistical models in NLP during the 1970s through the 1990s. These data-driven probabilistic methods offered a more robust way to handle the inherent ambiguity and variability of human language. A key development in this era was the introduction of hidden Markov models in the 1990s, which significantly improved the performance of applications like speech recognition and early machine translation systems. The rise of modern chatbots and conversational AI. The convergence of NLP with machine learning and later deep learning techniques dramatically transformed chatbots from scripted responders into more intelligent and capable conversational partners. A critical component of this transformation is natural language understanding, a subfield of NLP that focuses specifically on deciphering the meaning, intent, and context behind user utterances. Key NLU techniques that fueled this advancement: statistical models, early approaches like n-grams, and a provided foundational capability. Word embeddings. Techniques such as word-to-vector and GloVe, developed around it, revolutionized NLU, provided a way to represent textual data in a format that could be used for semantic search and similarity analysis. This allowed models to understand that king is to queen as a man is to woman, for example. As the use of these embeddings became more widespread, the need for efficient storage and retrieval mechanisms for those high-dimensional vectors grew, leading to the development of increased popularity of vector databases, widely used nowadays for RAG, retrieval augmented generation. Deep learning architectures. The deep learning era brought recurrent neural networks and long short-term memory networks, which excelled at processing sequential data like text. These were followed by transformer models introduced in 2017, such as BERT, bidirectional encoder representations from transformers, and the well-known GPT generative pre-trained transformer series, which enabled performance in understanding context, nuance, and generating human-like text. This model can analyze user input for sentiment, identify entities, and determine intent with far greater accuracy. This technological surge led to the development of mainstream conversational AI systems. Smarter Child, an early 2000s chatbot integrated into popular messaging platforms like IOL Instant Messenger and MSN Messenger, offered a glimpse of more interactive and functional bots. IBM's Watson, famous for its 2011 victory on the game show Jeopardy, showcased remarkable question-answering capability. The same year, Apple launched Siri, the first widely adopted voice-activated virtual assistant on smartphones, followed by Amazon's Alexa and Google Assistant, which further popularized conversational interfaces. The true agency. Understanding and responding to language is foundation, but for AI to manage business processes, optimize operations, and make strategic contributions, it must also perceive its environment comprehensively, learn from experience, represent knowledge effectively, reason logically, plan strategically, and act decisively. The development of modern AI agent is a testament to the synergetic advancements across several core AI disciplines. The Dartmouth Summer Research Project on Artificial Intelligence in 1956 stands as a historical moment, officially birthing AI as a field. Organized by pioneers like John McCarthy and Marvin Minsky, the workshop coined the term artificial intelligence and set forth the ambitious agenda of creating machines that could simulate every aspect of learning and intelligence, including language use, concept formation, and problem solving. While the intentional optimism for rapid breakthroughs proved premature, the Dartmouth workshop laid the theoretical groundwork and ignited the decades of research necessary to develop the practical tools. The foundational pillars of modern AI agents. Machine learning and deep learning. Machine learning fundamentally shifted AI from systems that were explicitly programmed for every contingency to systems that could learn from data. Deep learning, a powerful subset of machine learning utilizing artificial neural networks with multiple layers, has been particularly transformative. Early milestones like Frank Rosenwald's perception in 1958 considered the first artificial neural network capable of learning, and later breakthroughs such as likened 2012, which revolutionized image recognition, demonstrated the increasing power of neural architectures for AI agents. ML and deep learning provide the ability to adapt their behavior, improve performance based on new data and interactions, and effectively process vast amounts of information like text, images, and audio that are common in enterprise environments. Knowledge representation and reasoning. For an agent to act intelligently, it needs a way to store, organize, and utilize information about the world. This is the domain of knowledge representation and reasoning. Early AI research, influenced by systems like the General Problem Solver, GPS 1959, and John McCarthy by Staker, explored methods to encode knowledge for problem solving. The field evolved through the development of expert systems in the 1970s and 80s, which aimed to capture human expertise in specific domains using rules and facts, and frame languages, which provided structured ways to represent objects and concepts. Core knowledge representation and reasoning concepts include semantic networks, graph-based structures of concepts and relations, templates for stereotypical knowledge, production rules, if-then statements, and ontologies, formal specifications of concepts and their relationships within a domain. These mechanisms allow agents to possess and apply domain-specific knowledge, understand complex interdependencies, and make context-aware decisions. Recent breakthroughs, particularly the integration of knowledge graphs with large language models, are significantly enhancing AI agents' contextual understanding and reasoning capability. Techniques like K-begin and Qbert are pushing the boundaries of how machines can learn and represent knowledge effectively. Automated reasoning and AI planning. Automated reasoning equips AI systems with the ability to perform logical inference, make judgments, and derive new conclusions from existing knowledge. Its roots trace back to early AI systems like the logic theorists, which could prove mathematical theorems. AI planning, a critical component for agent autonomy, involves developing a sequence of actions or a strategy to achieve specific goals. This allows agents to move beyond simple reactive behaviors to deliberate, goal-directed action. The evolution in these areas has led to modern AI agents capable of multi-step reasoning. More complex problems are broken down into smaller, manageable parts. Reinforcement learning, which enables agents to learn optimal strategies through trial and error and feedback from the environment, and memory-enhanced architectures, allowing agents to retain and recall past experience to inform current decisions. These capabilities are fundamental for agents to autonomously navigate complex enterprise tasks, adapt to changing conditions, and execute sophisticated workflows. Robotic process automation, convergence with AI. RPA refers to software technology that emulates human actions to perform structured, repetitive digital tasks such as data entry or invoice processing. While highly efficient for rule-based processes, standalone RPA systems typically struggle with unstructured data, exceptions, or tasks requiring complex decision-making. The convergence of RPA with AI, often termed intelligent automation, enhances RPA's capabilities significantly. AI technologies like NLP and ML allow RPA bots to understand and process unstructured data, for example, extracting information from emails or documents, make more nuanced decisions, and learn from outcomes. For AI agents, this means they can orchestrate API bots as part of a larger, more intelligent workflow, effectively bridging the gap between cognitive tasks like planning and decision-making and execution of routine process steps. The combination of these technologies allows AI agents to operate across a wide spectrum of intelligence, from sophisticated pattern matching and prediction to complex planning, for genuine autonomous decision-making in novel and dynamic enterprise scenarios.